Now, let's go really have a more detailed stare at the graph node involved, because now this is where the rubber meets the road and you're actually doing real work. So in the MaxSwap plugin MaxSwap directory, there's a guy called node.c. Oh my God, it's a graph node, it's alive. So here we go. Things with graph nodes are you absolutely need to register them. You can do so dynamically long after the thing starts. The standard way for feature nodes is really to do them this way. The fields that you populate in this header function are in this descriptor object, whatever you want to call it, are pretty obvious. Dot function is the dispatch function for the graph node. It gets a name. The vector size, in the beginning of time, VLib, the vector engine, was intended to do very general vector processing where the vector elements are of whatever size. So one of the things you get to do is to tell it, okay, size of a U32. All of the packet indices that you process in this world are actually, unsigned 32-bit integers. The type names, a lot of people would say, well, why aren't you using uint32t? It's because that's fewer characters to type. I hate typing, and as you've seen, I type reasonably rapidly, but you don't get, unless you're getting paid by the character, there's no sense doing it. Graph nodes get names for obvious reasons. Like if we were to say show run, you'll see that the MaxSwap node here has run, and that it's actually gone and swapped 16 guys. One of the things when you're doing real work as opposed to messing around on a laptop with a debug image, you're going to care about is the number of clocks per packet. And 20,000 clocks per packet is not anything anybody wants to write home about. Now, needless to say, at a vector size of 1 in a debug image on a laptop, the timing data is accurate, but it's not going to be very impressive to anyone. So again, let's get back to the code here. So to do a graph node, you end up spitting it out. These are the .next nodes are static next dispositions that are set up during the init sequence that are bound together. There's a function called vlib node add next, which says I have 2 graph node indices. All of them have indices. I want to connect A to B. The control plane can even do that. Why would you want to do that? Well, if an interface is down, you may not want to bother creating an output node for it. At any rate, so that's the static setup canonically at the bottom of the file. Then here's the dispatch function. This is the guts of it. At the beginning of said function, you're going to say, give me a vector, ordinarily of packets, to process. How many n left from is the number of starts off as the number of elements you need to process. Next index. You remember I was mumbling earlier about speculation. Well, as these dispatch functions run and run and run, we just kind of say, look, the last place you were putting stuff is the first place you're going to put stuff this time. Not to worry about it. We'll fix it later if it's wrong, but you want to start with some guess as to where things are going. So while we still have stuff left in the vector, get next frame. Okay, remember next index here? What this guy's saying is, look, I absolutely need to have permission and to have everything set up under the floorboards to shove packets down the particular graph arc I'm telling you about. And we need to make sure that that node actually has a place to put stuff. Here's the beginning of the dual loop where you're saying, as long as I've got enough packets to do a prefetch 1 chunk ahead, and I've got 2 packets left in this game, I'm going to sit here in what I call the dual loop. This is the typical performance thing. You'll see all of this stuff is stylized, and across the entire set of graph nodes, they all look exactly this way. This structure has been beaten to death, and it'll keep you from having to do a whole lot of mechanics. When we're doing 2 packets, we typically, the first thing in here is prefetch is prefetch the next pair. VLib get buffer, what that's doing is it's taking a 32-bit index and going and getting hold of this thing, a VLib buffer T. Let's take a second and look at what the VLib buffer T looks like. And these are the actual pieces of buffer metadata. And they actually have Doxygen tags in them. But what it amounts to is current data is a signed 16-bit offset from the standard DMA target, data sub 0. We ask the device drivers to always shove data in, in what you're going to see below, which is a zero-length array, which is the ultimate DMA target. Now notice with the DPDK world, there's a nice little layer cake here, which is that the DPDK's buffer metadata lives above this stuff spatially in the actual buffers. Notice that we have the buffer headers and the body of the first chunk contiguous. It's a performance tune. A lot of people will do a linked list chase there. Pointer chases are not your friend when doing performance coding, and we work real hard to never do them, as you'll see as we go into the infrastructure a little bit. So current data, current length, pretty obvious stuff. That's how big the packet is, modulo current data. That as you advance current data forward, the overall length of the chunk shrinks. Some flags, tracing, next present, multi-chunk, total length valid. Invariably with the DPDK drivers, total length valid is set at the driver level, and you never actually have to go running around counting and taking cache misses to go find the next buffer. The buffers do form a linked list. The size we're using at the moment is 2048 because it's everybody's favorite at the moment. So for normal-ish traffic with normal-ish MTUs, you never really see chain buffers at all. On the other hand, all of the infrastructure is carefully set up to handle those cases. What else is recycled? Yeah, I don't want to talk about that at the moment. Free list index at the VLib level. There are potentially multiple free lists of packets. These comments are fairly good. Trace index is used in the tracing system. Clone count is whether the guy's been done. The opaque data turns out to be pretty important. This isn't the place to look at it. Again, this is down in VLib where it's a little funny to have the basic buffer structure defined. It's certainly funny to have P's thrown in it. The opaque and opaque 2 guys are used for data of local significance to be passed across subgraph arcs. That you'll see the IP stack uses it some to pass adjacency indices, but other subsystems in there use opaque and to a very lesser extent opaque 2 to pass things that are critical to know from node to node. When working in that area, you have to be a little careful not to wipe out subgraph arc metadata that you depend on. Like if you're a graph node and you're going to throw packets at IP4 lookup or IP4 rewrite, you better not mess up the IP opaques, or you better be setting them deliberately. One of the things that can be done that I'm going to show you in detail when we look at the IP4 stack a little later, assuming we get there, is that the particular fib that's used to look up on a per packet basis can be specified by setting one piece of metadata in a very particular way. Ordinarily, the lookup follows the interface, which is what you want to do 97% of the time. But if you're doing deliberate route leaking, for example, MPLS over GRE, it's quite common to say, I've received a packet in a VRF, I want to encapsulate that guy in MPLS over GRE, and I want to forward the packet through the default fib. The way you say, and through the default fib, is you go tickle one piece of metadata and throw the packet at IP4 lookup. That degree of freedom costs you about 1 clock cycle in the speed path, but it allows you to do deliberate route leaking. And it's kind of an important network-ish sort of thing. Again, back to the topic of buffer metadata, you want to be disciplined in your use of it. You don't want to waste a lot of stuff. One of the things that I've seen happen in software packet paths is that the buffer metadata grows to consume the entire city of Los Angeles by mistake. We try to be lean and mean in this stuff and to say, look, local significance only, don't go crazy with it. If you need another data structure that has a bunch of stuff in it, well, it's perfectly fine to put into the buffer metadata an index in an object which says, oh yeah, it's this session. Quite common to have 2 million sessions, quite common to paint into the buffer metadata you know, a 32-bit index in a data structure to go then look up later. But for God's sakes, no, you know, this is the kind of thing that needs great, you know, this structure is one of the absolutely performance critical things. You don't want to just dump random crap in here. So back to the code. I'm sorry, I get off on this stuff. You know, back to node.c. So vlib get buffer says go get me the next you know, +2 and +3 buffers. Prefetch the buffer header. That's just a canned routine that says, well, you know, who's buried in Grant's tomb? Please go prefetch the buffer header. Then prefetch some packet data. This clib prefetch operator, we'll get into clib/vppn for later, I hope, if we don't run out of time. The next thing we do here is we say, okay, where are the 2 packets that I'm currently working on going? And we're going to say basically they went exactly where the last 2 packets went. Then we actually go start working on the packets and swapping the MACs. So we've already pre-enqueued them to the next disposition, believing that, you know, against, you know, with all odds, that speculation's correct. This is a considerable performance improvement over every time going and doing a lot of thinking about it. So what we do is we'll grab the Ethernet header, and I'm not kidding you about this not being the fastest way to swap source and dest MAC addresses. I'm just doing it a byte at a time. You know, sorry about that. You know, it's the simplest thing, but the idea is in this place in the skeleton, when you're doing your feature, you say, oh, this is the Barrick says go process 2 packets at once, please, part of the loop. So that's what you do here. And we basically say, well, okay, this is the VNetified version of that opaque I was talking about a while back. VNet buffer sub v0. Let's go show you that one because it's important in doing real networking. VPP, VNet, buffer.h. This is where that, okay, yeah, I was asked to say, where is this file for VI people? It's in, you know, at the VPP level, VNet, and then buffer.h, which ends up declaring this epic catalog union of all of the local significance guys. You don't actually have to play this game. If you're doing something that you want to be totally private between your set of 3 graph nodes, there's no need to go actually paste something in there. The one thing you do need to do is, please, for God's sakes, don't mess up the buffer metadata that's going to, you know, that you're going to use when you throw the packet back at IP4 lookup or rewrite. These guys, you know, basically this is the buffer metadata union, and for multicast replication, for this, that, and the other thing, we union these guys together. There's also, you know, this is the IP6 map version of using the thing, and in all cases, you want the input and output interface slots to be available. So VNet buffer opaque T, an important structure. It is the buffer metadata. The opaque 2 guy has no formal contents at the moment. One set of feature nodes, I think carrier grade NAT ends up using them at the moment. They didn't even play the game of checking in their metadata. This is the kind of thing that's, you know, it's commonly done in network processor coding. It's a little bit of a, this file is where you'll get merge conflicts and where you must be careful. One thing I've asked people to do is to, at the top of this guy, make yourself an epic catalog of all of the union types. If you add a union type, add it here. What I do is to very specifically, as the thing boots, check to make sure the length hasn't exploded. Because if the length of the buffer metadata gets wrong, all of the shit gets unaligned, and you've just kind of taken Mark IV torpedo to performance. You absolutely don't want the size of the overall union to differ from what it thinks it is. So at any rate, please, if you're going to add something to the buffer opaque union, right there's the place to go with it. Back to MAC swapping. So here we're saying, what interface did this come in on? What interface do I want it to go out on? Well, pretty obvious stuff there. Here's the packet tracer hook. Predict false is just a predicted branch, which says, okay, we're supposed to be tracing these guys, and you saw what ends up happening. The add trace macro is again in the infrastructure. You always want to implement tracing, trace T. Okay, what I'm tracing here in binary is the next index and the interface. And here's the format function that you declare actually down in the bottom. See that format trace guy? This is when a graph node has contributed something to the trace. Here's the function you call. And this is just kind of hooking all the pieces together. And you remember when we were running it, we saw max swap, software IF index 5, next index 0. This is the guy that's actually in charge of doing it. That's supposed to be in every graph node. There are examples of doing optimizations where you trace a whole vector at once, if and only if any element is supposed to be traced. But you know, we've done the kind of simple thing here. Again, this is a case of the reason there's an Emacs skeleton is it'll remember all the boilerplate for you, and you can go back in and figure if you're doing foobar here, you know, you could change the printf string so that it's obvious in the trace. Nothing, no rocket science there. Again, so thematically what we've done is we've done some prefetching, we've swapped the MAC addresses, we've said send the thing back where it goes, and this NQ by 2 macro says, okay, I have 2 guys, here's where they go. Let's take a quick look at that ugly macro just so that you've said, yes, I've looked at it and I never want to look at it again. This, find G, I'm sorry. I normally have that bound to a function button, so I'm not fumbling around so much. What this guy does is it says, go say, you remember that guy next index I was saying was cached forever and ever on then as a place you're going to shoot stuff? It's actually an interesting variable, which is to say what we do is we say, remember, I've speculatively NQ'd these 2 packets where the previous pair were going. Now, what this macro works out is whether there were any mistakes made. And typically what you do is say, okay, next 0, the place I want packet 0 to go. Next 1, the place I want packet 1 to go. I've just turn it into an integer code. If it's predict false, meaning believe that you probably got it right, go in here and handle the various cases. We did an ABANQ, an AABNQ, or an ABCNQ. If thematically you're really switching from I'm always pushing to IP4 to always pushing to IP6 for some reason, you'll go through this relatively costly thing once, then you flip over that next index variable and the rest of them will just play nicely. Big disgusting macro, ends up being quite the performance tune. So in the average case, this VLib buffer NQ by 2 is about, a clock cycle or so to NQ a pair of packets. That generally you get the speculation right, and now you're ready for the next pair, prefetching a pair ahead. One of the tricks we use in coding is to say, okay, well, what would happen if the stuff that I'm actually prefetching takes a while to come back, and we're seeing in a performance trace that we need very badly to prefetch a little differently. One of the things you can do is to quote unquote increase the stride, which is instead of prefetching 2 packets, basically 0 ahead, you prefetch 2 packets 2 ahead. So what you end up having to do there is instead of looking at mumble sub 2 and mumble sub 3, you look at mumble sub 4 and mumble sub 5, so that it takes a little longer to warm the pipeline up, but you're ordering data from the load store unit a lot earlier. But that gets to be very, advanced tuning only after you've done everything else to make sure that your feature's really working right. This is the kind of stuff where you call me up on the phone, you call one of the Cisco guys who's been doing this stuff for a year up on the phone, and say, dudes, I've got this thing, it's functionally correct, I've done the dual looping, yada, 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 but the performance data still doesn't look right. You know, you ask people that have been doing this stuff for a while, well, what are some of the hints? One of the hints is to increase the prefetch stride a little bit. The other hint might be to take multiple passes across the entire vector. That when you run into a situation where the load store unit, you've just swamped it with stuff. Ultimately, again, as I was saying yesterday when I was talking to everybody in the planet, you run into cases where the load store unit just doesn't have enough outstanding prefetch slots or enough outstanding reference slots to do what you need. Then you can, you can prefetch a little further ahead. You can restructure the computation. You can change algorithms so that you're not hitting as much data. But that's really the limit when you've run the system out of load store opportunities. Again, networking is almost all very super load store intensive, and the bigger the tables, the more you have to prefetch ahead, or you don't get what you want. At any rate, so here's the dual loop, and then we come down, and obviously you might have gotten 3 packets. Well, what do you do with contestant number 3? And the answer is you do a singleton loop, which says as long as you've got work to do and there's place to put it, yada, yada, yada. Again, the speculation shows more clearly here, where you're just saying mumble sub-0 to next sub-0, which is, again, the frame object in the next graph node that this guy gets, swap a MAC address, yada, yada, yada. And here you do the NQ by 1. Put next frame basically updates the data structures. Notice that we haven't made much of an effort to keep the next node's data structure all hooked up. I should have said earlier, when you do, VLib put next frame, VLib get next frame, one of the things that secretly does is, remember about 2 hours ago when we were looking at the while one loop that sits and runs the graph dispatcher? These guys actually throw things into the pending frame vector, those couple of macros. And that's how your graph node has now done its thing, and it says, but but I'm not the end of the line, obviously. I want this stuff to go do something. Those 2 macros end up actually causing the next node to run. Increment counter, absolutely worth talking about. This is a per node debug counter, like when we were looking at it earlier running. Let's see if I get lucky. Yeah. Show. Oh, did I ever? Oh. Okay. I know why, because I ran it interactive in a window, didn't I? Oh yeah, there we go. At any rate, if we do, here we are. We ran the thing up a minute ago. Show error. There's there's the per node counter that you see right yonder in the code. Notice that we're really only doing the counter bump once. Counters are actually an interesting sport. When Damian talks a bit about the threading support later, one of the things about about the counters we do is that you could just bluntly say all the node counters are all the counters are are 64-bit and they all get atomic increment decrement. That turns out to be just manifestly stupid, because like it or not, atomic ops are expensive on commodity hardware. So what we really do is we'll bump a 16-bit non-atomic per thread counter. When that guy overflows, or when the control plane decides it needs to scrape them, we go aggregate them together and do a single atomic to keep the world being rational. At any rate, counters are they're very interesting. They're one of the differentiators between VPP and just a purpose-built, direct over the DPDK application, that we really work hard to have the right counters. What I've done here is to kind of automate the process of putting them together. All right, so that's a whirlwind tour through a skeleton graph node. Do folks have questions about the graph node coding that they don't think they're going to be able to work out later that I need to work on now? Because I don't want to leave this topic